Okay, this lesson is on volume by revolution, and we are using what I call the parallel method or the toilet paper method. Textbooks are going to call it the cylindrical shell method. So if you're trying to Google it or find it in a textbooks, look up cylindrical shells. One of the differences here, obviously, I'm calling it the parallel method, and that would be because we're going to draw our rectangle parallel to what we're going around. And when we do that, the shape is going to now be different. It's going to be a cylindrical shell. And so imagine this dark blue outside as being that shell. It's like a soup can label. So to get the area of that, you're actually using circumference times height. And so when we use the parallel method, we use 2 pi r h. Whereas when we use our perpendicular method from the previous lesson, we were making circles or discs, CDs, and we were using pi r squared. So everything today is going to be 2 pi r(h), whereas the pi r squared was from the previous lesson. Try to keep those two separate, okay? And like I said, I typically refer to it as the parallel method, but if it helps you, call it the toilet paper method, because it should remind you maybe of a toilet paper roll. Okay, these steps may make a little bit more sense since you've gone through that first type of revolution. We're going to draw our typical rectangle again, but this time we're going to be parallel to what we're going around. We're going to draw this time what I call radius and height arrows. We will still decide whether we have dx or dy the same way. This time we will decide if you have one or two integrals based on whether or not the rectangle is touching the x or y axis. You're not always revolving around the x or y axis, but you may be touching it with your rectangle. And so that's the main difference here in deciding that. Then we will set the integral up with our limits and solve. And again, remember we're using 2 pi r(h). Okay, so 2 pi r(h), and our limits are going to match the dx or dy just like they did before. And again, you can solve these with the fundamental theorem, or you can solve them with your calculator using math number 9. Today we're going to have a different arrow than just our height arrows. We're going to have a radius arrow. And so I'm kind of drawing you one of those situations where we talk about adding and subtracting and things like that. The radius arrow is going to be plain, kind of. It doesn't have the function involved with it. If you are going just from the axis to something, that arrow is just x. If you come from behind, that's when you say a number plus whatever that x is. And again, we're not saying the function. It will literally be a plain x. If you're coming from the right, it's kind of like before. It's the number minus, but now I have plain x when referring to the radius. If my radius arrow is an up or down arrow, if I'm coming straight from the axis, so from this point here, I'm going to call it y. If I'm coming from below, that's when I'm going to say a number plus that. If I'm coming from above, that's when I'm going to say a number minus that. We're going to use that same example again just to get that practice in with the setup, because it is kind of easier to be consistent as we're learning the concept. So it's the y squared equals x cubed, or x cubed equals y squared. We're going to 8 on the y-axis and 4 on the x-axis. The lower region is region 1 and the upper region is region 2, the same as our previous lesson. Okay, so our first example, we're going to be revolving region 1, our lower region, around the y-axis. And so the y-axis is over here. I'm revolving this way. The difference today, when I draw my rectangle, I'm going to draw it parallel to what I'm going around. Y-axis is vertical. My rectangle is going to be vertical. Okay. Now I'm going to draw height and radius arrows. Height arrows are kind of like what you think of. They almost come second nature. The height of this rectangle is from the axis to the function. Your radius arrow is going to come from what you're revolving around to your rectangle. Now, I was just talking about that radius situation. Since we're just coming from the y-axis this way, this is going to be called x, plain old x. Okay. You'll notice we have a vertical rectangle, so we're in dx, and we're going from 0 to 4. And since our rectangle is touching the x-axis, we should only have one integral. And again, that also is going to match the number of height arrows you can draw. So I have one height arrow, one integral. So integral of 2 pi r h, so you have two things to fill in. It's a dx, and our x limits are 0 to 4. Now, as we discussed, since our radius comes from the y-axis to the rectangle and it's nothing behind that, it's plain old x. Your height arrow is what's touching the function. So that's where the function comes in, and you need the variable to be x. So you need it as x to the 3/2. So there's your setup. If I were using the fundamental theorem to solve, I would go ahead and simplify this first and probably take that 2 pi out front so I could think about it a little more clearly. Okay, now example 2, we're going to take region 2 around the y-axis, and region 2 is that upper region. So this big region around the y-axis. So the first thing I'm going to do is draw my typical rectangle parallel to what I'm going around. Since I'm going around the y-axis and it's vertical, I'm going to draw a vertical rectangle. Remember, I'm going to stop it at 8 because that's where region 2 ends. Okay, now I'm going to draw my height arrows. My height arrows are going to come from the axis. So from the x-axis, I can draw to the bottom and the top. My radius comes from the axis I'm going around. I'm going around the y-axis, so here's my radius. Again, that's a plain x because I came from the axis, not from behind it or from above. So plain x for my radius. Since I am not touching the x-axis, I have to have two height arrows, which means two integrals. So I'm going to do an integral of 2 pi r h minus the integral 2 pi r h. My radius is x. I've already figured that out. It's x in both cases. The height arrows are what changed. This is a dx rectangle, so I'm going to use my x limits from 0 to 4 and put a dx at the end. So 0 to 4 dx, 0 to 4 dx. Now I just have to figure out what those height arrows are and fill in the heights. So long minus short again. So a long arrow goes from 0 to 8. So that height is 8. The short arrow goes to the function, and the function needs to be in terms of x to match our limits. So x to the 3/2. And there's our setup for example 2. In example 3, we're going to revolve region 1 around the x-axis. Let's see if you can draw that picture. Hit pause. Okay, this should be what your picture looks like. Since you're going around the x-axis, you draw your rectangle in region 1 parallel to the x-axis. Your radius is going to come from the x-axis to the rectangle, so in this case it'll be a plain y. Your height arrows have to come from an axis in this type of problem, so they come from the y-axis to the bottom and the top of your rectangle. So this tells me I need two integrals, and again we're using 2 pi r h. And since this is a horizontal rectangle, we're using dy, and so our y limits are 0 to 8. So 0 to 8 dy, 0 to 8 dy. We already have figured out that our radius is y. Now we just have to figure out our height arrows and what they're touching. Long minus short. The long one goes from 0 all the way over to 4, so the long one is 4. The short one goes from the axis to the function, so the function needs to be in terms of y to match our limits, so it would be y to the 2/3. And that's how we set up example 3. Okay, let's go to example 4. We're going to revolve region 2 around the x-axis, region 2 being this upper region. So the first thing is I'm taking that around the x-axis, going here. The x-axis is horizontal, so I need to draw my rectangle horizontal. That means my radius comes from the x-axis to that rectangle, and so that should be a plane y. I can draw one height arrow because I have to come from an axis. So I only got one height arrow. That means I'm going to have one integral. So I'm doing one integral, 2 pi r h. Since our rectangle is horizontal, it's a dy, and so I'm going with y limits from 0 to 8. I already have figured out that my radius is a plane y. My height arrow goes from the axis into the function, so it touches the function, and I need it in terms of y, so it'll be y to the 2/3. And that is how we set up example 4. Alright, now example 5, we're going to go with something a little different. We're going to go around x equals 4, and that's that vertical line over here at 4. So the first thing is I'm doing region 1, which is the lower region. So I'm taking this region around this line. There's my rotation arrow. Now, because I'm revolving around a vertical line, I need to draw a vertical rectangle parallel to that. Your radius always comes from what you're going around. So this time our radius is going to come from the right. And if you'll remember, when we come from a right, it's always number minus. The number was 4 because that's what we were at. And then when it's horizontal like this, it's x, which should make sense because we have a dx rectangle. And our height arrow, we can only draw one of those in. So I'm going to have one integral. So one integral 2 pi r h. As we just said, we have a dx, so we're using x limits 0 to 4 dx at the end. Our radius, as we discussed, is 4 minus x. And then the height arrow is touching the function. So I'm using the function in terms of x, so x to the 3/2. And that's how we set up number 5. Okay, we're also going to do something a little different for example 6. We're going to revolve around x equals -2, which is back here before the y-axis. So right here, and that's a vertical line at -2. We're going to revolve region 1, which is that lower region. So this region around this line, again, we're going to have a gap there in the middle if you're trying to visualize it. Since that is a vertical line that we're going around, draw a vertical rectangle in region 1. And your height arrow, you can only draw one. Your radius is going to come from the line that you're going around. Since we're coming from back here to the left, that radius gets 2 plus whatever, and then again from the axis to the thing, it should just be an x. Okay, so that radius is technically going to be 2 plus x, since we're coming from that far left side. I can only draw one height arrow in, so I'm only going to have one integral. So I'm going to do the integral 2 pi r h. This is a vertical rectangle, so it's dx. My x limits for region 1 are 0 to 4. Don't over stress about that. So 0 to 4 dx. We've already determined that our radius is 2 plus x. Then we just have to figure out what our height is. And since our height's touching the function and our variable is x, that's going to be x to the 3/2. And that is how we set up example 6. Our last example using this particular function, we're going to revolve region 1, that lower region, around y equals -2. We've done some x's, not a y today. So y equals -2 is going to be down here. So it is a horizontal line at -2. Okay, so again, region 1 being this almost triangular region, smaller region below the function, taking that around the -2, there'll be a gap here if you're trying to visualize it. And since we're using the parallel method, I'm going to draw a parallel for my rectangle. My radius is going to come from what I'm going around to my rectangle. And this is one of those cases where I'm coming from below, so that distance, we went from -2 to 0 there, that's 2 plus, not -2 plus, it's a distance, so that length is 2. Then if I'm going from the axis to the rectangle, that is y. So this radius will be 2 plus, I don't know why I put 2 pluses in there, be 2 plus y. My height arrows have to come from an axis, so they've got to come from the x-axis, or excuse me, the y-axis. And again, that region 1 ends at 4, so that one's going to end at 4. Because I had 2 height arrows, or the fact that this is not touching an axis, means that we're going to have 2 integrals. And so 2 pi r(h), 2 pi r(h). And this is a horizontal rectangle, so it'll be a dy. And I use my y limits from 0 to 8. We've already determined that our radius is 2 plus y. So both get the radius 2 plus y. The long height arrow goes from the axis to 4, so it touches 4. The short one touches the function, so I'm going to use the function. I need it in terms of y, so y to the 2/3. And so that's how we set up one that comes from below, and that is our last regular example with this x cubed equals y squared. For our final example, I wanted to show you what a multiple choice question might look like and how you can figure out, without doing all of the work, what's going on. So here we're going to change the function up. Y is going to be x minus 3 squared, which is a parabola that has been moved right 3. And so we're just going to look at that region between there and the x-axis, that first one, and I've drawn a terrible parabola, but you understand what it should look like. And if it's been moved right 3, it's going to touch the x-axis at 3. So we're looking at, again, this region down here, and we're revolving around the x-axis. The problem here is that you have both setups. A couple are in the perpendicular method and a couple are in the parallel method. So this is the perpendicular method, this is the parallel method. So the first thing I'm going to think about is, if I'm in the perpendicular method, I would be drawing perpendicular to what I'm going around, so my rectangle would be vertical. So I need to make sure that those are dx's, and they both are, and they both go with x limits 0 to 3. Okay, so that makes sense. We'll talk about what goes inside of these now as well. They've pulled that pi out front. So if you remember, when you do that pi r squared formula for a perpendicular setup, our r in this case would be that function. Well, the function is squared, so it would be x minus 3 squared squared. So if it's going to be one of these two answers, it's going to be the one with the 4th power. So we're going to star this one and we're going to cross this one out because of that squared power. Now, let me come back over here and consider the parallel situation. Those would be parallel to the x-axis. So these should be dy's. Well, none of these are dy's. And the limits should be 0 to 9. So none of these are 0 to 9. So this is going to have to be B because it's the only one that matches what's going on. Another way you can also tell down here is even at this, the radius should be there. This one doesn't have a radius. These have radiuses of X when they actually should be Y. So you can look for those kinds of things as well. And then there's differences in the power if you're trying to compare those. So this power doesn't match either. So this one's a clear choice. You don't have to do all of the math to be able to figure out which one it is. And that concludes our lessons on volume.